Hi everyone, this is Liz, first year PhD student in astronomy. Well, it's almost the end of the first year. And happy Pride Month to everyone. And today I came with a review for this paper called A Disk-Based Dynamical Constraint on the Mass of the Young Binary DQ Tau. So first a few words about the object. So DQ tau is a young spectroscopic binary, meaning that so it's a closed binary that was identified as a binary based on the observations of spectral lines and how they move in the spectrum. And young meaning it has a circumbinary disk around the system. So from these spectroscopic observations, it was found to have around a 16-day rotation period. And on top of that, based on observations of the optical, in the emission lines, in the radio, it was seen that it has also variability in luminosity with the exact same period. And it was later on in the works tied to its accretion, and there's also a number of works investigating what's exactly at play there. In short, it's magnetic field of the stars, the accretion that is driven by magnetic fields of the stars. So overall it presents an interesting system precisely because of this periodicity, because in theory, or not in theory, in practicality as well, there is a bunch of systems that have all types of variability, of accretion variability, but the problem with them, quote unquote problem, is that when the bursts happen is a bit unpredictable. But with this system, you can exactly time when it should happen. And that kind of makes it a sort of a lab rat for studying how accretion variability impacts the disk. And you can time your observations precisely to the epochs when it should happen. The only offset is that even though the time moment of the change in luminosity can be predicted somewhat, the amplitude is a bit random. So you can kind of time your observations, but you'll end up with a burp instead of a burst. And also, and you can kind of guess it from the time scales, the bursts themselves are not very powerful, so the impact on the disk is quite limited, and it's kind of it cannot be substituted with much more powerful bursts. It cannot be used to study them because it's a different type of object. But nonetheless, it's a very interesting object that I'm kind of also doing a work on at the moment. And in this work, they took some ALMA observations of this object to try to make constraints on the mass of the binary in the center of this YSO. So they took observations in very popular lines, 3 COI isotopologues, this exact transition 2:1, and they did it with a very good spectral resolution, like 0.1 kilometer per second. This is channel maps here of intensity in CO in 13. So the idea of the method here is that that you can see through the emission of CO how the gas disk rotates. and it is assumed that the rotation of the disk is driven by or defined by the mass of the central object. So studying the rotation of the gas disk, you can infer what's the mass of what's in the center. In idea, only CO is enough for that. You need only one line for that. But it's always too good. But why they did 13 CO and C8, here is basically, I suppose, it never hurts to have more data, and it will be only helpful to constrain it further. And these isotope logs are less abundant, so you can see a bit deeper in the disk. So it's good to have them. However, they did not get a good detection on those lines, unfortunately. And so they proceeded only with analyzing CO. On top of that, they also took an archival result from paper Mathieu et al. 1997. It was probably one of the first papers on this binary, where they did optical spectroscopy, and from the Doppler shift of optical lines, they measured radial velocities of the components. And this is like a very classic, very traditional method in the variable star community, who do multiple star systems. And this is basically, it's all long ago solved, how this dependencies of radial velocity on the phase should look, and how it is defined by the mass, or by the masses of the system and the eccentricity. Like, you can get a whole orbital solution from here. This is like a very powerful method and very well fleshed out. And so they took this data as well to kind of revisit it with the new, more fleshed out, more precise methods, to get overall like a combined estimate. So that's what they did. So first with ALMA, what they did is, to fit the observations, they assumed some very simple model, very standard, this surface density power law, logical structure from vertically isothermal hydrostatic equilibrium, which comes from a power law temperature profile, everything very classic. On top of that, they do a Keplerian velocity field, and that is something that is defined by mass. And that all together with inclination and the position and so on and so forth goes into Radom C3D, which is a radiative transfer tool which can give you emission line, line emission and then they later on also kind of do a Fourier transform to get visibilities and then to compare it with actual observations. So they get this a bunch of parameters describing this very simplistic model, and they run MCMC sampler to get points to where you evaluate the model, and then compare how it deviates from the observations. And essentially that's the plot on the left. Of course there should be more of this parameter correlation plots in IDEA, but because they used like 12 parameters, as you can see from this table, but the goal of this paper was to constrain mass. So, and mass kind of defines only the velocity field, only the rotation. So it does not really have any correlations with other parameters at all. And the only correlation that they found was with inclination, because it makes sense. Inclination also kind of impacts the radial velocity in a very understandable way, I suppose. And so as they focused on the stellar mass, this was the only thing of relevance here. So they plotted this, and here they found. So this is I guess I'll call it correlation plot, like a bite of corner plot, basically showing you what's the best fit values are. The brighter it is, the better the fit, or the closer the fit to the observations. And they find here a correlation between them that is sort of like a constant value. On the other hand, you have also constraint from RV, and RV method, by the way, gives you also, it cannot give you mass and inclination separately. It can only give you like a combination. It can give you mass multiplied by sine cubed of inclination. So this is what's plotted here. Also one thing. So for all this parameters, I think they did uninformed priors, except for inclination, where it's not that much informed. It's just the one that comes from spherical coordinate system shenanigans, assuming because it comes from the fact that you want your disks to be, you assume your disks to be randomly oriented in space, and that actually makes that demands in the spherical coordinate system, not the uniform distribution of the angle, but uniform distribution of the cosine of the angle, if I remember correctly. So it's kind of that kind of prior. And also with distance, so with distance they did not vary it freely. They took the value for that was measured in some other paper for the Taurus star forming region where this binary is located, and did a Gaussian prior. So the distance is pretty much fixed here, and we will come back to that later. So if you take RV, and I think this is the new RV result, which we'll see further on. If you combine them, or take that as a prior, this limitation, then you get this distribution. Oh, and also, not only take that as a prior, but basically, when you do inference from the ALMA data, or using ALMA data, you get the inclination that is there is the inclination of the disk, because you trace the gas component of the disk. But in RV, you are observing the stars themselves. So what you get, the inclination that you get there is the inclination of the binary orbit. And those are not necessarily the same. So, and here on this plot, they kind of assumed coplanarity, which means that basically the binary orbit and the disk lie in the same plane, and hence have the same inclination for us. And with that, you get a bit stricter values here. And a bit different. So if here it was if you can see here, 160 degrees, and then a mass of 1.3. Also not very precise, as you can see. It's like minus 0.27 plus 0.46. That's actually they explain because if you also see from the inclination, which is pretty well constrained, that this is almost a face-on disk, so that kind of makes it a bit hard. Makes it a bit harder because the radial velocity components are not as well. They're not as good as they're not as wide. The velocity does not change as widely as it could because of that. So that of course impacts the estimate. And another thing is that there was a molecular emission from like some cloud that had the same systemic velocity and kind of contaminated the observations. And that also kind of reduced quality of the estimate. So, and with the RV, so again, they took the data from the archival data. They did not. I think maybe they had like I think they said like they did 3 new observations or something. But either way, mostly archival data. So what they did improve upon, so it was done by, I think, 2 teams of telescopes. So the first one on the left is CFA, so from Harvard's Center for Astrophysics. There, the observations managed to capture both radial velocities of both components. And the other was LMK, which is like 3 telescopes. I don't remember which ones, but and for that they had only data of radial velocity difference between 2 components. And in the original 97th paper, what they did is they did initial fit only based on CFA data, and then took those results, and based on that results they separated radial velocities of components for LMK and then did a combined fit. But that kind of created a certain bias, of course. In this paper, however, they decided not to do that, and they fitted CFA separately and also LMK in its original form of radial velocity difference. And overall, they got a very, very similar results. They got like the full orbital solution and so on and so forth, very similar to what was in the 97th paper, but they improved the uncertainties like a factor of 2 to 5, which is very nice. And then, yes, that was used here. I think that's their results. And so in the discussion, first they discussed, again, basically this combination of the results from ALMA and from RV. So from ALMA, as you could have seen here, you see that they found this kind of correlation between inclination and the mass. That's that. So it turns out in a form of mass multiplied by sine squared of inclination, being some constant value. That's assuming a certain distance. A distance is needed here because you fit the line emission, which scales as distance squared. But on the other hand, from RV, which is independent of distance, by the way, you get this. And as you can see here very clearly that if you assume coplanarity, these 2 things equal, you can, by dividing them, get a sine of inclination. And that's basically, I think, what was done here. They just divided the 2. You get an inclination, and from inclination, you get the mass. And this is kind of their final estimate here. On the other hand, what you can also do, and what they did is they released the constraint on the, like they noticed in their data, even at before that there is a certain dependence of the mass estimate on the distance. And so they tried releasing the constraint on the distance, but enforcing coplanarity and kind of doing a prior from RV at the same time. And with that, they get a bit of a different estimate on the distance. They call it basically the dynamic estimate of the distance, which is a bit further out than this measurement for the, not for the DQ tower, but for this star forming region. And that's actually like, I was a bit surprised to see that, because it turned out to be like, it's not a very precise estimate, but now in the future, 9 years later, after Gaia did so many measurements, and now we know a much more precise value, which is 195 parsec. That turned out to be much closer than this. So yeah, that's a cool result, that they also could get such a constraint on the distance, which kind of was prophetic in a way when the Gaia came, that it is indeed further out, and the Gaia's measurement is within this error bars. So nice. And then in the second part of the discussion, they also compared with a third method of getting a mass, which is not dynamic, but instead is based on evolutionary models of pre-main sequence stars. And what you do there, so you have these models which depend on the someone's writing me, which depend on the star. So what you do there is they took the photometry, and based on that photometry, they tried to fit the parameters of the stars, like effective temperature and so on and so forth. And then when they got them, you could put them on the, well, basically what do you need, like luminosity and temperature, to put them on the HR diagram, sorry, not HRT, HR diagram. And then from that, you can plot the track and get the age and the mass. So they did that, and they got a value that is also quite close to the mass that they obtained dynamically, which is cool. So the conclusions here is that we used two dynamical methods. We got mass from the RV. Is one of the solutions, is a part of this orbital solution. You get a mass ratio between the components, and from that you can get masses of individual components. And so the conclusion here is that we did that, we got the result. It's they correlate with each other. I mean, they kind of correspond to each other. What's the right word? Like, they agree with each other and also with the other method, which is not dynamic. So it's cool. We can do that. We also did. They also had like 2 papers on other objects before that. Also was a success, and cool, very nice. And yeah, I agree. It's a very neat paper, not a very large one. Everything was clear. And having orbital solutions for such a star where its binarity is tied to the accretion is very important, and they did that, and they got this mass. However, I would not suggest to use these masses in particular, because again, these masses are assuming the prior estimate of distance, and it scales with distance. So if you want updated masses for a new distance, which is 195 parsec, it will not give like that much of a big difference, but still, you should check out a bit earlier papers. And I will actually, on the next week, there will be a paper review on a more recent paper, which I think acknowledges that. Yeah. So, but overall, thanks for providing the orbital solution and the scaling with distance. That's really cool, really good. Thank you. And thank you for listening to